multi-party computation. Today, Professor Prabhakaran will talk about correlations in cryptography. So,
thanks, Nilthara. Thanks for the generous introduction, and thanks to the organizers for inviting me. It's great to be here. Okay, so I'm going to give this talk, which I'm trying to keep most of the crypto out of it, even though there is cryptography in the title. Trying to focus on things which are, I believe, of broader interest. So correlations in cryptography. By the way, I should also mention that it's going to be a baby-themed talk. So you'll see Alice and Bob babies. So what are correlated random variables? So for now, for two-party setting, which is what I'll mostly focus on. So the two parties, the babies, are observing something, which is some common process, but they get different things out of it. But Alice gets X, Bob gets Y, but they are correlated. So that's what we mean by correlated random variables. The process is randomized, so there's some distribution, some joint distribution over these XYs. For example, it could be something like, X was generated maybe by Alice and somehow randomly, and she sent it to Bob through some noisy channel, and Bob got something which is correlated with X, but not necessarily the same as X. Okay. So this kind of correlation comes up in communication, information theory quite a bit, but there the focus is usually to get rid of the noise, right? Or even in places like learning theory, you're trying to get to the root of it. You're trying to learn what is the real randomness. So you're trying to get the full picture. That's not quite how we are going to look at it in cryptography. So to kind of quote from an influential work by Kerper and Killian way back in '88, so from our point of view, an ideal communication line, where Alice sends X, Bob gets Y, is a sterile, cryptographically uninteresting entity. Noise, on the other hand, breeds disorder, uncertainty, and confusion, and is cryptographers' natural ally. Okay? So cryptographers like the fact that this X and Y are not the same. They are different, and that they're different. And we are going to focus on, I said X and Y coming from some process. Well, it's not going to be a natural process for us. It's something we design. So we have a finite alphabet for X and Y. And this entire correlation can be represented as this bipartite graph, where on the left you have this entire alphabet, what all possible observations Alice could make, what all possible observations Bob could make, and in between, for any pair XY, there is some probability. P of XY, the probabilities add up to 1. That's a joint distribution we are interested in. To make it a little more concrete, here's an example, which is an important example. It's called Oblivious Transfer for some reasons which hopefully will become clear towards the end. Here is a correlation. It's very simple. There are 3 bits involved. So B, X0, X1. They're uniformly randomly chosen, so 8 possibilities. And Alice gets X0, X1, and Bob gets this bit B and X sub B. So if B equal to 0, he gets X0 and 0. Otherwise, he gets 1 and X1. Okay. So we'll see why this is interesting. Or we'll see some things about this. But maybe I should tell you why this is interesting for cryptographers. And that has to do with something called secure two-party computation. Okay? So if you have not seen secure two-party computation, forget all about the correlations I'm telling you today. This is more important. This is the thing you should remember from this talk. So it's a very cool primitive that cryptographers have come up with, starting from early 80s. And what is the idea? So these babies have some inputs, and they want to compute some joint function of that, right? And they could do a protocol for that. Alice could send some messages to Bob, and vice versa. And at the end, they both get the output of the function they are trying to compute. But that's how real world works. What their babies would like to be is in this ideal world, okay? In this magical world, where Alice gets her input, Bob gets his input. They just send it to this idealized magical entity who takes the 2 inputs, computes a function, gives it back to them, gives the answer, just the answer back to them. What is so cool about this magical world? Alice learns nothing about Bob's input other than what she can infer from her own input and the output, and same for Bob. So each party is assured that the other party doesn't learn anything, even when they're, so if this is a secure protocol, even when they run this protocol, they're assured that, so Alice is assured that Bob learns nothing more than from this protocol than what he could have learned in this world, okay? And vice versa for Alice. So that's secure two-party computation. Can we do it? It seems very magical. Well, depending on how well you want to do it, the answer depends. The short answer is yes, we can do it. But if you don't want to make computational hardness assumptions, which we don't want to in today's talk, then you need some help. And the help comes in the form of correlated random variables. So you set up some correlation between Alice and Bob ahead of time. Then they don't need any more computational hardness. They can just go ahead and do some magical protocol, and that will have the effect of doing this secure computation. Okay. And today, for our parties being babies, we'll stick to honest but curious babies. Honest and curious sound like good things, but for cryptographers, curious is bad. It's like the baby will go out and tell everyone whatever the baby saw in their house. Not quite the best behavior, but it's honest. You tell them something to do, they'll do it. Okay. So you could also talk about a malicious adversarial behavior where you don't trust the baby to be even following the protocol. Right? We won't get to that today. Okay. So now that I've told you what secure two-party computation is, and that's one of the reasons why Oblivious Transfer, OT, has become very important. So there is a sequence of works in the early 80s or the mid 80s, starting with Yao's Garble circuit, which showed that if you are given OT, you can securely compute anything. So Yao originally needed OT and one-way functions, and he gave this protocol which is secure against in the honest but curious model. Subsequent work by Goldrake, McCulley, and Wigderson works even against the active corruption model, but for us, more interestingly, just given OT. Now, without any computational hardness, no one-way functions, you can do two-party computation, or in fact, any number of party computation, just using Oblivious Transfer. Okay? And subsequently, Killian actually showed that even for active corruption, that's the case. Just given OTs, you can do any protocol securely. You can, compute any function securely. Okay. So, what makes OT special? So there are many things about OT which makes it very suitable for these protocols, and I'd like to tell you about something that is special about OT. And to tell you about that, or tell you about correlations, or some things about correlations in general, let's step back and talk about something kind of simpler about correlations, and that's called common information. So what's common information? Well, Alice got X, Bob got Y. They didn't get the same things, but by virtue of the correlations, there are certain things that they might both be able to tell you, right? So something that they both know. That is common information of a correlation, of a correlated random variable. For instance, let's see what OT can tell you, or what is the common information in OT. So you might say, okay, Alice has x0, x1, Bob has b, xb. x0, x1, b are all independent of each other, but maybe we should consider xb as something that is common information. They both know xb, right? Well, not quite, because when I say common information, I mean that it's a piece of information not just that they both happen to know, they should know that they know it. Okay, and this kind of self-awareness, I don't trust babies have it, so I'm going to change babies to normal people, bigger people. So I want to define this common information in a way that both parties know it, but they also know they know. That sounds like too philosophical, but it's actually very simple. How would you define it? You just say, okay, that's some piece of information they both should be able to output locally. So Alice looks at her X, outputs this piece of information, Q. Same with Bob, and these both Q's should be the same. Okay, if they can do that, then I will say Q is common information. Okay. So now you can go back and ask, what is common information in OT? XB? Well, not quite, because Alice can't output XB, because she doesn't know. She has both X0 and X1. She doesn't know which one is XB, right? So it turns out OT has no common information. Okay? And actually, it's not a particularly deep statement, because it's very easy to look at a graph like this and say, what is common information? Well, what is common information is essentially, so the most that these two parties can agree on is, without any error, so the Q should be the same always, is which connected component their X and Y falls in. So in this case, I don't know if you can see, there are two connected, disjoint connected components, one in which this, so when they got X and Y, they both know that the connected component is a blue connected component. Okay? That's the best they can actually agree on. If you think a little bit about it, anything else they can agree on without error is just a function of which connected component they lie on. Okay? The edge XY lies on. Okay, so that is that's common information, and with oblivious transfer, as we'll see later, it's a single connected component. So there is nothing they can agree on without error. A question that is of interest, especially, yeah. The bipartite graph was a correlation. So every edge is a probability of xy. Okay, I should also mention, thanks for asking, if that probability is 0, I don't put the edge. Okay, so that's why I can talk about disconnected. It's not a complete bipartite graph. I have only non-zero probabilities here showing up as edges. Does that make sense? Okay, so when I get x, I have no idea whether your y is this or that, right? There is some possibility it's this and some possibility it's that. But I know that whatever it is, it's in this blue connected component. Right? Okay, so so the best they can agree on is the connected component. Okay. Now, one could ask, okay, that sounded like I wanted this 0 error. There should be no probability of error. But often happens in information theory, if you allow many copies of this common random variable, maybe you can do a little better. And if you allow a small error, like if you say, okay, allow you n copies, you should output something that you agree on, except with probability 1 by n, let's say, or negligible in n, things like that, right? Turns out, doing all that doesn't really help. Okay? And these were classical results in information theory by Gauge and Corner, and subsequently sharpened by Witz and Hausen, basically saying that this is a common information even if you have n copies. All you can do is, for each copy, you can just say what connected component you are in. There is nothing else you can compute which has more entropy than that. Let me actually, to give you a flavor of, okay, so in particular, what Gauge and Corner is saying is that if there is a single connected component for this XY graph, so it has 0 common information, and then I give you many copies of that. Okay, so some edges, they become very tiny probability. All edges actually will start having in the bigger graph. So you should think of a bigger graph where, I don't have a picture for this. If I had took two copies of XY, my alphabet squares, right, on both sides. And my edges become kind of thinner. Each edge is smaller probability. It's about x1, y1, and x2, y2. So each node here is now x1, x2, and y1, y2. Okay. So in that graph, there are or in general, when you have n copies, you have x1, x2 up to xn as a node here, and y1, y2 up to yn as a node here. And the edge between them corresponds to all xi, yi being given to the two parties. It has very tiny probability. So you could imagine that, okay, maybe there is some error, but that error is because of some unlikely events, some tiny edges happening, and maybe they can agree on a common random variable without with only this kind of tiny error. That's not quite the case. So if I start with an xy, which is a single connected component, I take n copies of that, independent copies of that, I get some huge graph, and even in that huge graph, it's a single connected component with very tiny weight edges. It's still the case that you cannot agree on a common random variable other than the, it's still the case that you cannot agree on anything except if you allow large errors. So let me actually just say all that once more in a terminology that might be more relatable to many of you in terms of spectral graph theory. So this is a observation we had in a paper, but Witzenhausen's proof already does this. There's just a kind of a recasting of that proof in more computer science terminology. So this is a graph we are looking at, or if you look at a graph and you ask, and imagine there are certain nodes on which when Alice gets them, she will output 0, and certain other nodes when she gets them, she will output 1. Okay? So you can draw this partition. These are all the nodes where Alice or Bob is outputting 0, and these are all the nodes where Alice or Bob is outputting 1. The edges that are crossing here correspond to error. Right? So Alice outputs 0 and Bob outputs 1, or vice versa. And what we are really interested in saying is that the mass of those edges in any cut will stay high. You cannot make that mass tiny as long as these mass of each of these components have to be large. Okay. And you can analyze that by looking at what's called the Steger constant. So it's the weight of a cut SS complement, so weight of edges crossing it, and normalized by saying neither of these cuts can be too small. Right? So I want each part to be large, and I'm interested in seeing how small the mass of the crossing edges can be. So if you're, so the probability of error is directly related to that quantity. And what we are really asking is a question, what happens when I take this n-way product of this graph? Okay, so which I'm denoting using this funny notation, because it's not quite a normal graph product, it's a bipartite graph product, corresponding to taking these independent copies of the correlated random variable. And it turns out, this very standard spectral graph theory stuff, you can look at an eigenvalue, this second eigenvalue of some metrics related to the graph, and the Steger constant is fairly tightly bounded by this spectral, this eigenvalue. Okay, why do you care about that? Because the eigenvalue behaves in a very nice way when you do this graph product. Okay? You can show that under this kind of product, the eigenvalue doesn't change at all. And that tells you that the error doesn't go down much at all. Okay, even if you take n-way product, for any n. Okay. So it doesn't matter if if you're not familiar with the spectral graph theory, the bottom line of that is that this common information is something fairly robust, and it answers this question. If I give you many copies of xy which do not have common information, can you generate common information? Can you flip a common coin without interaction? And the answer is no. But that leads to kind of a bigger question. What if I was not asking you to output common random variable like this q, both sides? Right? Maybe I'm asking you to output some other correlation. I give you xy from some correlation. I ask you to output some uv from some other correlation. And that's a question of what's called non-interactive simulation. Okay? And it's a question in the information theory literature. Okay, so given samples from some source correlation, and you can have any number of samples, independent samples, and the source correlation doesn't have any common information. Why do I say that? Because if it had common information, they could have anyway sampled this UV from that common information. Okay, if you have enough common randomness, they you just sample U and V both, and Alice outputs U, Bob outputs V from that. Also, I don't allow interaction for the same reason. If Alice and Bob could communicate, Alice can compute UV, send V to Bob, right? You don't want to do that. So yeah, the question is non-trivial when you are given some source correlation which has zero common information, and you are not allowed any interaction, and you are trying to output some target correlation. And what we just saw is that if the target correlation has some common information, then hard luck, you won't be able to sample it. Okay, so target correlation also shouldn't have any common information. You cannot generate common information without interaction if you are not given common information to begin with. So it actually turns out to be quite a hard problem. There are some impossibility results using looking at something called the hypercontractility of these correlations, and more recently there were some results showing that actually this problem is decidable, which is to say if I give you correlation XY and correlation UV, you can run some computational process which will terminate in finite time and tell you if this is possible within a margin of error that you prescribe, if it is possible to sample. Not the most satisfactory solution in the sense that we still don't know. Does that mean there are many correlations which cannot give other correlations, or we don't know the landscape of the correlations. We just know that, okay, we can decide given any two particular correlations. Still, it's a very heavy machinery that I'm not familiar with. This is work by Madhusudan and his students, and that's Elkin and Nossel, and so this was in Fox 2016, that's Soda 2018. I've not had a chance to look at these papers, but I'm sure it's very interesting stuff, just that it doesn't give a very intuitive answer to the full landscape yet. Okay, but still, we understand that problem reasonably well, somewhat. Here is a different perspective, though, on that problem, okay, where we understand it much better. And okay, so the problem is, this whole previous problem was meaningful only when I did not allow interaction. Given interaction, it kind of trivialized the correlation, right? Alice can sample UV and send V to Bob. So in some sense, it makes the correlation trivial. Every correlation is equally good or bad. Well, not quite so if you are coming from a cryptographic point of view. Okay, so this is our cryptographic lens on this problem. Because it's no good if Alice samples X0, X1, B and sends BXB to Bob. It's no good from a cryptographic for our secure multi-party computation. If Alice is our curious baby, she knows too much. She will end up knowing Bob's inputs potentially when they do a secure computation protocol using this OT. So for something like OT to work, it's important that parties know exactly what they're given and nothing more. Okay? Which is not the case from the just sampling problem that I was posing previously. Okay, so now things change quite a bit. Okay, so now it turns out that there's a much nicer landscape, or something much easier to understand. There's a dichotomy. There are trivial correlations and there are complete correlations. What do I mean by a trivial correlation? Trivial correlations are those which can be securely sampled by interacting parties. Okay, you allow interaction and everything, but it should be secure still. Okay? And intuitively, the only things you can do like that without any outside help, without any correlations given to a priori, are trivial things. Okay? And I'll tell you what trivial is in a second. And the other class are the highest possible kind of complexity. They are complete in the sense that given enough copies of this correlation, such a correlation, you can sample any other correlation securely. You need interaction, but you can sample any other correlation securely. And what are these two classes? Well, the trivial correlations are those where all the correlation is because of common information. So there is no residual information, where residual information is a gap between your correlation measured, for instance, as mutual information, and the common information, the entropy of the thing I was describing previously. Okay, so all your correlation is because there is a piece of common information and everything else is independent of it. Independent given this common information. Those are the trivial kind of correlations. Yeah. Yeah, so there's an entropy of that Q. Yeah, entropy of the Q. Yeah, entropy of each component. And this dichotomy extends to active adversary model too. You need much more sweat and blood to get there. But philosophically, again, this is what makes OT special, for instance, right? That it has correlation or mutual information beyond just common information. Yeah, so that's what makes OT special, that it has positive residual information. So it's not just OT. Any such thing, right? Any correlation which had positive residual information is complete. You could have used it. It's just that OT comes in a much more nicely packaged way. The only way we know how to use the other things, or not only, but the way we know how to use the other things is first get OT out of it, and then use OT. OT comes in a much more easy to use way. But philosophically, this residual information tells us the whole story for at least the cryptographic purposes. However, it's not the most robust quantity. Or you could ask, is it telling us telling us everything about correlations we care about? So you could ask, for instance, if I perturb the probability distribution given to me slightly, what will happen? Things like mutual information and entropy are robust to that. They're continuous. In some sense, Witzenhausen's result was saying, yeah, this is also continuous. If you have common information 0, you perturb it a little bit, even after taking n copies. So you perturb it, you're allowed to perturb more and more. The more copies you take, you'll still stay 0 common information. Okay, that's what Witzenhausen said. But not in general. That's for some special case of correlations. In general, things can go really wrong, right? So you have some correlation like this. So it has 2 connected components. So it has 1 bit of, so if they're all uniform, basically has 1 bit of common information and 1 bit of mutual information. Okay, and I put a very tiny probability, move a tiny probability mass to say, okay, maybe these 2 points can occur together. Suddenly there is only 1 connected component. Suddenly the common information has disappeared. Mutual information stays about the same. So the residual information just jumped. Okay, it's kind of a weird behavior of residual information. It's not quite stable, continuous. So you could ask, maybe we should step back and look at a bigger picture, and maybe we'll see where this fits in. And that's what I want to show you for the next few minutes, a bigger picture. So how many of you have seen this picture? So this is just showing entropy and mutual information of 2 correlated random variables, right? So very useful picture. This is entropy of x given y, entropy of y given x. This whole thing is entropy of x, entropy of y. And the overlap is the mutual information between x and y. It's kind of a bogus picture. It's like a Venn diagram. The area corresponds to these measures, but still a useful picture. So going to use that. So what is the trivial correlation I was referring to earlier? A trivial correlation is essentially of this form. So there are 3 parts, P, Q, and R. So 3 independent random variables, P, Q, and R. X is just P and Q. Okay, you get both P and Q. Y is Q and R. So Q clearly is the common information. And other than this common information, there is no correlation between X and Y. Right? P and R were independent and independent of Q. So that is what a trivial correlation looks like. Okay? Q, this random variable Q captures all the correlation. But it's not always the case that you can attribute all the correlation to a physical random variable. Okay? And that is a gap when, that we are talking about. So there may not be a queue that fully captures this overlapping region, this I of x, y. So we want to measure, how far is our correlation from being trivial, from having this form where there is a queue that fully captures that common information. Or another way to say that same thing is, how hard is it to capture the entire correlation precisely using a random variable? Okay. So what we were earlier trying was something like, we got this queue which was both inside x and inside y. Right? Alice could output it, Alice could deduce what it is, Bob could deduce what it is. So it's a random variable which is completely inside x and inside y. So that is, but we took the largest possible. It doesn't necessarily fill in the whole thing. Okay. You could look at it from another side saying, okay, let's take the largest or the smallest random variable in some sense of smallest entropy, and which covers this entire region. Okay, these are all things you could make sense of. But what all would you try? Well, why not try everything? So let's consider an abstract random variable q, okay, which I am drawing in this picture. The picture becomes even more bogus when there are 3 random variables, but never mind. And let's ask, how well this random variable captures this overlapping region exactly. Well, in this case, as you can see, it doesn't capture it exactly. There are some leftovers. So there's one region here we did not cover. What is that region? That region corresponds to mutual information between x and y given q. So I'm going to use some information theory, quantities. Doesn't matter what they are for, if you don't know what they are. It's just that, it's like standing on the shoulders of giants. The whole information theory, entropy, mutual information, they're really nice quantities. We take them for granted now, but they work out nicely often. So for now, I'm just going to use them as black boxes. So this is a meaningful quantity. This is a particular mathematical formula that intuitively measures this region. Right? How much correlation is left between x and y after q is given to you, or after q is accounted for. Similarly, there are other regions here. Here is a correlation between x and q, which is not captured by y. Okay? So that is mutual information between x and q given y. And there is another symmetric quantity, mutual information between y and q given x. These 3 quantities together tell us how badly q captures the correlation between x and y, okay? Or how well or how badly it captures. So the question of how far is a correlation from being trivial is essentially how close to 0, 0, 0 can this triple come? Is there a q that can simultaneously make all these extra regions 0? Right. Okay, does that make sense? So if you are trivial, there is a q such that all these quantities are 0. In that PQR, that q made all of them 0. And given an arbitrary xy, the question is how good a q can you find that makes this as small as possible? Now, how do you measure a triplet, how small it gets? Well, you could think of some norms and whatnot, but we are just going to keep the whole region. Okay? So I'm going to look at the entire region, and I define this what we call the tension region. Okay? This is joint work with Vinod Prabhakaran from a few years back. So the tension region is, go over all possible q's conceptually. Try all q's jointly distributed with xy. And for each q, you get a triplet like this, ABC, right? These 3 quantities. Plot them in the 3D space and see what it looks like and see how far it stays away from the origin. Okay, that's the tension region. And since we are interested in how far it stays from the origin, I'm going to take what we call the upward hull. So let me show you that. So the upward hull is just, this. So this is the tension region. The tension region is actually some convex shape like this. I care about how far it's from the origin, so I'm just going to take the upward hull. That makes certain things convenient. Okay, so that is a tension region. Any questions? Does that make sense? Okay. So given any xy, I can plot this three-dimensional region, and somehow that captures something about the correlation, how non-trivial the correlation is. If the correlation is trivial, this shape will be the entire positive octet. Okay, you will be able to hit the origin. Further you are from the origin, and we can show it's a convex shape and everything. And further you are from the origin, the more cryptographically interesting it is. It has correlation which is beyond common information. Okay, so it actually generalizes notions of common information that are already in the literature. I mentioned Gauge-Corner earlier. They defined the Q that I was talking about earlier is a Gauge-Corner common information. Okay? And the quantity here is the residual information I was talking about, the intercept here, okay, with one of these axes is a gap between the mutual information and the Gauge-Corner common information. There's another notion of common information, like a dual notion by Wiener. So Gauge-Corner asked how much, so you're given xy, you're trying to produce qq. How much qq can you produce for a given amount of xy? You could ask, okay, you are actually given qq, common information, and you're trying to produce xy. How much qq should you be given? How much common randomness should you be given so that without any further interaction you can produce xy? That is Wiener common information. Okay, so the bigger box I was drawing a few slides back, this one. That bigger box out there, which entirely covers this region, corresponds to Wiener common information. And that also shows up in our region, in the tension region. This length here, which you would draw some 45-degree line there and so forth, but this length here is a gap between Wiener common information, which is always larger than the mutual information, and the mutual information. Okay. So it's kind of this is a bigger picture, exactly what I was trying to show. And this whole region is essentially continuous, except, of course, I said these quantities are not continuous. So what happens is that you put that epsilon edge into a correlation, this whole thing tilts a little, okay, and this can shoot up quite a bit. Yeah. Okay, so there are two other intercepts here. So this is not an intercept. What I was showing was the line, you draw the 45-degree line, and that length is this. Okay, but these two intercepts are also interesting quantities. In fact, the three intercepts were identified before our work by Wolf and Wurschlager, and shown to have some cryptographic properties, which I'll mention in a bit. Okay, but they're all special cases of now. Once you see the bigger picture, you can just forget all that and just say, okay, there's a whole picture here. Okay, so why do you care about this? So what I want to do, how much time do I have? Okay, I'll try to quickly tell you a couple of interesting things about tension and then something else. Why we care about tension is that there is a monotonicity theorem we can prove that a secure protocol cannot increase tension, in the sense that you start with some view xy, you talk to each other, your view changes, a lot of things come to your view, and you produce an output securely, uv. So your view went from being xy to uv. In that whole process, this region could have only been getting closer to the origin at every step. Okay? So a secure protocol cannot increase in the sense that it cannot make it into a higher region, smaller technically. It also has nice behavior in terms of when you take independent copies, it adds up. Okay? So if I take n copies of xy, you just scale this picture by factor n. And why we care about all that is this gives us a way to show bounds at the rate at which, so given n copies of xy, you want to produce m copies of uv, what is the ratio between n and m? Right? So we can lower bound this rate. And by looking at this tension region, and just mentioned that that subsumes all prior rate bounds by like Dodis Mikali long time back started this question of trying to find rates of reductions, Wolf-Schlegel identified that these 3 intercept points, they identified it differently, but turns out to be the same thing, have a monotonicity property, the same monotonicity property. Okay, and they use that to bound, and with the tension region, we can do better than that. Okay, last thing I want to mention about tension is it has something to do with communication complexity too. So why? Where does correlations come into communication complexity? Communication complexity is a question where Alice and Bob have x and y, and they want to compute some f of x, y. Okay. The trick is look at this thing as a correlation, x, z, y, z. Okay. So x, y are the inputs. Suppose they come from some distribution. You could even have them being independent, x and y being independent. So at that point, you have no tension. At the end, you manage to compute z. You have x, z, y, z. Suddenly, this, if we just looked at that as a correlation, it has a lot of tension. Okay. So but what I told you earlier, I told you the final views cannot have any more tension than the inputs. Okay. This is not a secure computation, so that's okay. So you might end up with z and a lot of other junk, right? So your view cannot have tension because of the other junk. But that is the crux. So where did all these other, so there must be other junk in your view that made your view have much less tension than this x, z, y, z by itself would have had. If you had magically found out the answer z, and that was added to your view, your tension would have jumped up. But since you did it using a protocol, and we know in the protocol the tension cannot increase, your protocol must have accumulated a lot of information about each other's variables, inputs, that removed this tension, or that prevented from creating this tension. So you can use that to get a bound. You can actually say, okay, in fact, you can do something slightly fine-grained. You can define the communication rate region. So how many bits Alice has to send to Bob and Bob has to send to Y. You can write that think of that as a region. What you can show, the bound you can show is that the region lies inside essentially this region. Okay? Cheating a bit, that's assuming what you start, so I defined this T0 to say in this plane, okay, the region in that plane. And if you start with x, y, which are not independent, you have to kind of adjust for that. But morally, the communication can only be inside this region. So if this region, if you have a lot of tension in x, z, y, z, so this region for x, z, y, z. If you have a lot of tension for x, z, y, z, then your communication has to be that much. Okay? And you can say it's not just that it has to be that much, it has to be Alice has to send this much and Bob has to send this much. Okay, so there is a whole literature on information complexity for communication complexity. This basically kind of rediscovers or slightly generalizes that notion, but coming from from a somewhat different point of view. We could also use tension to low bound communication complexity in secure computation, and we had a result a few years back, but I won't go into that. Okay, so the last thing I want to say, actually I have two things to say. So I'll say, okay, first thing in the last two things I want to say is that forget tension. Just ask this question of, we're trying to find complexity measures for functions. So you're thinking of a function family, right, with various size inputs. And generally you could ask this question, what is the complexity needed, right? You can look at Christo's book and you'll see like there are time, space, there are all these notions of complexity. You could add one more to that. You could ask, what is the cryptographic complexity of a function? By which I mean, or you could say, what is the OT complexity of a function? By which I mean the number of OTs that you need to compute a function f, okay, function family f as a function of the input size. Okay, OT is not supposed to be special, and it is not. So we know that asymptotically you can, at constant rate, you can go from any non-trivial correlation to any other non-trivial correlation securely. So OT is not important. And it's the same even if you ask this question, when I say securely compute, you can just ask honest but curious, or you can ask against active corruption. There also the complexity doesn't change much. Okay, so turns out actually it's a very hard problem. It's harder than giving circuit complexity low bound. Why? Because there's an old result, Goldreich-Weinisch, which we now think of as the GMW protocol. It's a refinement of that. It says that if I give you a small circuit for a function, you need OTs only essentially as many as the number of gates in that circuit. Okay, so cryptographic complexity is smaller than the circuit complexity. It's a lower bound on circuit complexity. So to give lower bounds on cryptographic complexity would be giving circuit complexity lower bounds, which we know is a very hard problem. Well, maybe cryptographic complexity is a very bad lower bound for circuit complexity. We know in some sense it's not very tight. They're not like they're equal quantities. There are certain regimes where cryptographic complexity can still exponential, but can be smaller exponential than circuit complexity at the worst extreme. But in general, I believe cryptographic complexity will be exponential for most functions. Unfortunately, unlike circuit complexity, we don't have a simple argument, even the existential result, saying that there is some function family with cryptographic complexity that's even superlinear, but forget exponential. So that's an open question. I think it's a very nice open question. We don't have any tools for that. Tension that I mentioned, cannot do better than linear lower bounds. Of course, the real challenge would be to find an explicit function family that will subsume the problem for circuit complexity. So it's not something I'm saying is an easy problem, but it may actually, who knows, give a different approach to looking at circuit complexity. Okay, now the last thing I wanted to say was everything I said so far, correlated random variables, itself is very interesting, but a special case of something even more interesting. And that something is a randomized function. So what is a randomized function? It's not just xy that Alice and Bob get, but they get xy in response to some inputs they give. Okay, so w and z. Okay, and there is some distribution, conditional distribution of xy given wz. So that is a randomized function. So you have a variant of, just to give a quick one thing about it. You could think of OT as a function too. Okay, a slightly different thing, of course. And the standard formulation of OT as a function is the following. Alice gets x0, x1 as input. Bob gets b as input. And the only output is to Bob, which is xb. So same three random bits, x0, x1, b. But now you have a notion of, Alice doesn't have any output. Everything is an input. And Bob has two possible inputs. And within each input, he can get an output. Okay. But I'd like another formulation of OT, just relabeling this, which corresponds to what's called oblivious linear function evaluation, also used in cryptography quite a bit, especially if you want to go beyond bits and talk about larger arithmetic circuits, or when the values are in field, in a general field. So here, Alice's input is x and a. So again, everything is Alice's input. Bob's input is y. So same thing. But what Bob gets is a b such that a XOR b is equal to xy. So it's what we call an additive secret sharing of the AND of x and y. Okay. Actually, there's an even nicer way that I like. I realized last week when I was making these slides, it has a name in the quantum information theory literature. It's called Popescu-Roerlich box. Okay, so again there, it's more symmetric. So it's kind of better for some things. Again, same picture, a XOR b equal to xy. But now Alice also has an output. So Alice is an input x, and a is an output for Alice. Okay, so Alice and Bob have inputs x and y, and they get outputs a and b, which each bit a and b by itself is random, but a XOR b is equal to xy. Okay, and it's interesting because it's a non-signaling function. What is a non-signaling function? means that, of course, your inputs and outputs are correlated, right? But if you just, if you look at just the other party's inputs, your view, your actual input-output combination, doesn't tell you anything about the other party's input. Okay? It can tell you something about the other party's input and output combined. So you kind of mentioned this last thing without making further connections. So there's something very famous in quantum mechanics called CHSH game, or spooky action and, at a distance. So question is this, suppose Alice and Bob are given this XY, okay, of the inputs of this Popescu or box, and they're asked to produce AB, okay, such that A XOR B equal to XY. If they can do it, they can do it according to the right distribution also. It's not a problem if they have common information. So they are given common randomness. Okay, now you're asking, can they do this well? And there's a famous inequality called the Bell inequality, which essentially says you cannot do it very well. Okay? There's some limit on how well you can do it. And the interesting thing in the quantum setting is that you can do a little better than the Bell inequality if you have quantum entanglements in addition to common randomness to begin with, right? Okay, so that's not just correlations. We are talking about randomized functions, and with randomized functions, you could ask the non-interactive simulation question that I was talking about. No security yet. Okay, so Alice and Bob are given access not just to the correlation, but the function, and they're trying to simulate some other function. Well, it doesn't make sense to ask this non-interactive simulation question if they could interact via this function, right? Even though they cannot talk to each other directly. Well, the importance of non-signaling, or one thing about non-signaling functions is, if this function is non-signaling, they cannot communicate through this, through that box. So then it's still a meaningful question to ask, which non-signaling functions can you derive given a non-signaling function? Okay, without communication, without requiring security. And turns out there is a result saying that PR box that we saw is actually complete. So given enough copies of the PR box, it's a non-signaling box, you can compute any other non-signaling box. I don't think anybody has asked this question if security is also needed. Okay, so I guess I'm out of time, so I'm just going to conclude. The conclusion is very simple. Correlations are fascinating. Connections to cryptography, information theory, communication complexity, computational complexity, quantum information. But I don't think we understand them very well yet. Everything I talked about was for two parties. Go beyond two parties. We have some results. We have some generalization of tension with more than two parties, but not the real deal. Okay, non-interactive simulation, cryptographic complexity ones, all of those things are open for two parties. You go to randomized multi-party functions, they are even more so on both counts. They are more fascinating, and I think we understand them even less. Like a baby sitting on a unicorn. I think it's a complex object to study. All right, so that's all I wanted to say.